Good evening children, this is Padma from G.K.Jain schools. We shall start with exercise 2.7 of complex numbers from 12th max. It is involving two different concepts, Euler form of a complex number and polar form of a complex number. So we will try to work out all the sums of exercise 2.7. We will be seeing about this exercise in this class and also in the next class. Let's move on to the topic now. Let us go through the basics of this exercise once again. Hope you all remember the polar form, its definition, that is z is equal to r into cos theta plus I sin theta. Okay, so x plus iy will be denoted in the polar form, and also this tabular column without which we will not be able to find the theta value, whether it is lying in the first quadrant, second or third and fourth quadrant. Okay, so this tabular column is very important, followed by which we have some properties of the arguments. Argument is nothing but the theta. Okay, so we have all these properties. You have to go through the properties also, and then comes the Euler's form, that is e power I theta, which is equal to cos theta plus I sin theta. So the form is z is equal to r into e power I theta, and we have to go through the properties of polar form also. Let's move on to the rest of the sums in the exercise 2.7. Exercise 2.7. So in the previous class we did till exercise 2.7 first sum. So today we will go ahead with exercise 2.7 second sum. Find the rectangular form of the complex numbers. So we need to find the rectangular form of the given complex numbers. Cos pi by 6 plus I sin pi by 6 into cos pi by 12 plus I sin pi by 12. So what I have to do, first I can combine these two cos theta plus I sin theta together, that is adding the angles alone or adding the arguments alone. Cos of pi by 6 plus pi by 12 plus I sin of pi by 6 plus pi by 12. Now when I am taking the LCM, this becomes 12, and here it will be 2 pi plus pi divided by 12, and here also 2 pi plus pi divided by 12. And what is 2 pi plus pi? That is 3 pi. 3 pi by 12, 3 pi by 12. And when I am going to cancel it, I will get it to be cos pi by 4 plus I sin pi by 4. And now what is pi by 4? That is 180 by 4, right? Cos pi is nothing but 180. So 180 by 4 is nothing but 45 degree. So what is cos 45 and sin 45? It is 1 by root 2, 1 by root 2. So the rectangular form of the given complex number is 1 by root 2 plus I by root 2. Now the next sum, second subdivision, cos pi by 6 minus I sin pi by 6 divided by 2 into cos pi by 3 plus I sin pi by 3. So first this 1 by 2 is disturbing, so we will take the 1 by 2 outside and we will write the expression alone, that is cos pi by 6 minus I sin pi by 6 divided by cos pi by 3 plus I sin pi by 3. Now after writing that, what we are doing, I am going to write this, listen carefully, I am going to write this pi by 6 as minus pi by 6, because cos of minus theta is cos theta. Cos of minus theta, when if the theta is going to have minus sign also, cos has the nature of absorbing the negative sign. So what will happen to that? Cos of minus theta is cos theta. So I can write this cos of pi by 6 as cos of minus pi by 6. Whereas sin theta, when you write sin of minus theta, it is minus sin theta. So that's why we have changed the sign to be plus here. Whereas in the previous step, it was minus here. So when I am taking the minus, this minus goes over here. So sin of minus theta is sin theta plus sin theta. So we have written it over here like this. And then what we will do, we will bring this denominator to the numerator. So what will happen to this? The numerator, when it comes to the numerator, it will have a power like minus 1. Then minus 1 can be brought inside the argument, which will make it as minus pi by 3, and this will also be minus pi by 3. So now what we will have, cos of minus pi by 6 minus pi by 3 plus I sin of minus pi by 6 minus pi by 3. Now take the LCM. What will be the LCM for you? If 6 is the LCM, here if you multiply by 2, here also will multiply by 2. So minus pi minus 2 pi by 6, minus pi minus 2 pi by 6. That is minus 3 pi by 6 minus 3 pi by 6. That is minus pi by 2 pi by 2. What is pi by 2? 90 degree, right? So 90 degree. Now we saw in the first step also, that is cos of minus theta is cos theta, and sin of minus theta is minus sin theta. So this will become cos of minus theta is cos theta, and sin of minus theta is minus I sin theta, and cos 90 is 0 and sin 90 is 1. So 1 into I becomes I alone, and we have a minus sign here, so it is minus I, and outside we are having a 1 by 2, so it will be minus I by 2. Clear? Is that clear? So this kind of sums will be asked in the 3 marks. Now we will move on to the third sum. In third sum you are having 2 subdivisions. This third sum is very important sum, and it is frequently asked in 5 mark also. Both the subdivision together they will ask in 5 mark. See, if The given hint is if x1 plus iy1, x2 plus iy2, x3 plus iy3, etc. up to xn plus iyn is equal to a plus ib. We have to show that first subdivision is x1 plus iy1, x2 plus iy2, x3 plus iy3 plus etc. up to xn plus iyn is equal to a square plus b square. So how to prove that? First we will take the given concept, what they have given, x1 plus iy1 into x2 plus iy2 into x3 plus iy3 etc. up to xn plus iyn is a plus ib. So we will take modulus on both sides. So when I am going to take the modulus, I will apply the modulus on left hand side and also on the right hand side like this. And then as per the property of modulus, I can split the modulus. So this will be like modulus for each term now. That is modulus of x1 plus iy1, modulus of x2 plus iy2, modulus of x3 plus iy3 etc. up to modulus of xn plus iyn is equal to modulus of a plus ib. Now what is the purpose of taking modulus? Taking the square root. So this will become square root of x1 square plus y1 square into square root of x2 square plus y2 square into square root of x3 plus y2 square, y3 square etc. Now after the square root, obviously we will take squaring on both sides so that we can get rid of the square root. So squaring on both sides, we are getting it to be x1 square plus y1 square, x2 square plus y2 square, x3 square plus y3 square etc. up to xn square plus yn square is equal to a square plus b square. So we have arrived at the first result. We will move on to the next second subdivision. Summation r equal to 1 to n tan inverse of yr by xr is equal to tan inverse of b by a plus 2k pi where k belongs to the z, that is complex numbers. Now given x1 plus iy1, x2 plus iy2 plus x3 plus iy3 etc. up to xn plus iy1 is equal to a plus ib. So this is the common hint given for both the subdivisions. So we have written that. Now we are going to take argument on both sides. Here what we did in the first subdivision, we were taking modulus on both sides, and here we are applying or taking argument on both sides. Now when I am taking the argument is similar to the log. When you are going to apply logarithm, log a b, that is product rule, using that you can write them as log a plus log b. Similarly, argument property says that when I am having the product, I can write them in the sum. So argument of x1 i1 plus x2 into x2 i2 into x3 iy3 etc. up to xn iyn is equal to argument of a plus ib. Now the product can be splitted into addition, that is sum. Argument of x1 plus iy1 plus argument of x2 plus iy2 etc. up to argument of xn plus iyn is equal to argument of a plus ib. Now there is another property. When you are applying argument to the complex number, argument of x plus iy can be written as tan inverse of y by x, that is tan inverse of the imaginary part divided by the real part. So I will apply that to each and every terms over here. So this will become tan inverse of y1 by x1, this will become tan inverse of y2 by x2 etc. up to tan inverse of yn by xn is equal to tan inverse of b by a plus the argument, the general argument is 2 plus 2k pi where k belongs to z. So hence we have proved that summation r equal to 1 to n, that is when r is taking the value x1, x2, x3 etc. up to n. That is what we are summarizing here. Summation r equal to 1 to n tan inverse yr by xr is equal to tan inverse of b by a plus 2k pi where k belongs to z. Now we will see the fourth sum. If 1 by z, 1 plus z by 1 minus z is equal to cos 2 theta plus I sin 2 theta, show that z is equal to I tan theta. So this is very important 5 mark sum. So first they have given 1 plus z by 1 minus z is equal to cos 2 theta plus I sin 2 theta. So I will consider 1 plus z by 1 minus z where z will be substituted as x plus iy. So now what happens, wherever z is there, I will substitute it as x plus iy. So now I will group the real parts and imaginary parts. So this will become 1 plus x plus iy, and this will become minus has to be taken inside 1 minus x minus iy, that is 1 minus x minus iy. Now I have to take the conjugate, that is multiplying by the conjugate in the numerator and denominator. So it is minus sign here. So we have to multiply by the plus sign on numerator and denominator. Now I can multiply 1 minus x into 1 plus x, 1 minus x into iy into 1 plus x, I into I is I square is minus 1. So minus y square, because y into y is minus y square. And here you are having a minus b, a plus b. What is that? A square minus b square. Now we will multiply inside 1 into x, 1 into 1, 1 into x minus x, x square. X and minus x will get cancelled, and here you can write as it is and y square. Now again there is a square plus b square. Why we are getting plus b square? It is actually a square minus b square, but you should be thorough with this concept. Since I square is there, when it is squaring, I square will become minus. So minus into minus will become plus. Now again we are going to multiply this inside y into y minus xy plus y xy plus xy. So xy and xy will get cancelled. So we are getting it to be 1 minus x square minus y square plus I2y divided by 1 minus x square plus y square. So 1 plus z by 1 minus z is equal to, we are separating and writing the real part and imaginary part. That is 1 minus x square minus y square divided by 1 minus x square plus the whole square plus y square, and the imaginary part, that is I2y divided by 1 minus x square plus y square. Now what will happen? It was given in the question that 1 plus z by 1 minus z is equal to cos 2 theta plus I sin 2 theta. So my cos 2 theta will take the real part, will be equated to the real part, and sin 2 theta will be equated to the imaginary part. So what happens? Actually the proof contains tan theta. Z is equal to I tan theta. So we have to make sure that we will get tan theta over here. So what we'll do? We know sin theta by cos theta is tan theta. So we'll do it as sin 2 theta by cos 2 theta is equal to, accordingly this expression will also be written in the division. So obviously the denominators will get cancelled. So we'll be having sin by cos is tan 2 theta is equal to 2 by 1 minus x square minus y square. You name it as 1. Now they have given, we have to prove that z is equal to I tan theta, right? We have to prove that z is equal to I tan theta. So we'll start off with that itself. We know that z takes the value x plus iy. Now transform this I tan theta, which means you are having only the imaginary part, which easily makes you understand that the real part has become 0. So x plus iy is equal to 0 plus I sin theta. That is x and 0 are the real part, and iy and I tan theta are the imaginary part. So x takes the value 0 and y takes the value tan theta. So what we'll do from this derivation, we'll substitute wherever x and y as 0 and tan theta. Now substituting that, I am getting it to be tan 2 theta. So hence proved. So this is how you have to do this sum. This is very important 5 mark sum. We will continue with the rest of the sums in the next class. Thank you, children.